Good morning. So today's lesson is about heating and cooling curve. So we already know the three states of matter, and we know that we can go from solid to liquid by melting the solid, or from liquid to gas by evaporating it, from gas to liquid by condensing, and liquid to solid by freezing. In fact, this is all represented by something called the heating curve. Okay, so today we will discuss the heating curve of water. What is a heating curve of water? It's a curve that graphically represents the phases, so the phase transitions that a substance undergoes as heat is added to it. So as we increase the energy, the heating energy, how is the temperature affected? Okay, so starting from the very basic stuff that we already know, we know that an increase in the temperature, or when we heat a system, so we're increasing the temperature of the system. Increasing the temperature of the system means that we're increasing the kinetic energy of the molecules. Now, each and every molecule will increase the kinetic energy. And so we say that since heat depends on the potential energy and the kinetic energy, both of them, but temperature depends on only kinetic. Since kinetic energy is increasing, hence the heating, or the, if you want, the total internal energy of the system will also increase. Okay, so if we're increasing one factor out of two, then the whole system will also increase. Yeah, so let's now look over what we already have over here. So as you can see, we have a solid that starts from a negative value since we're below zero. So the negative value, let's say it's minus 15 degrees Celsius. Molecules are now in an ice solid state of matter, and we start to apply heat to them. So as we apply heat, we can see how the temperature is increasing linearly. So when I say temperature increasing, remember that I'm talking about the kinetic energy. So it's as if you zoom inside the solid. You'll see how the molecules that were stationary, or like not stationary, they were vibrating in spot, they start to gain kinetic energy, so that each and every molecule will start to vibrate more vigorously. Until what will happen? Until the temperature of each and every molecule will reach the melting point, which is 0 degrees Celsius for water. Okay, so if I copy this and I want to see the behavior of the molecules now that they are in the transaction phase, in the melting phase, going from solid all the way to liquid. So if I zoom in, I'm gonna, as we said, that temperature means increasing the kinetic energy. At this point, as you can see, the temperature remains the same, so we have a constant temperature during this phase. When I say constant temperature, means that the kinetic energy has reached the maximum amount. So particles will no longer vibrate more vigorous, they will just absorb more heat energy. And so as they absorb energy, it's as if we're filling them with this enough energy needed for what? Needed to break the bond with the molecule and become free. Okay, so even if one of them increased the heat, has enough energy to break free, this will not start to gain temperature, once again, until all the system has now the same internal. And so now that the system has enough energy to overcome the attractive forces, and they can move with respect to one another. So as more heat is added, we can see that temperature remains the same, but even if temperature remains the same, the energy absorbed by the molecule is increasing. So the heating is increasing. And eventually, these molecules will break free, and so they will be arranged as if they are in the liquid state, move past each other, and some vibration. And yes, now we have what? We have a liquid. Okay, so that's the first phase, the melting phase. Now the second phase, which is the boiling, is as like the same concept of melting. Okay, so once again, now that the whole solid turns into liquid, so these molecules will keep on increasing, absorbing heat, increasing temperature until they reach the boiling point. Now we know that the boiling point is 100 degrees Celsius. So what will happen during this phase? Once again, temperature will not increase anymore. So the vibration, the average kinetic energy of the vibration will not increase, but the energy absorbed is still, the system is still absorbing energy. So this, we can see it by seeing how the molecules are absorbing heat in order to what? In order to overcome, once again, the force of attraction between each other, and they break free and they turn into a gas. Okay, now the arrow of the gas is much larger as they can move freely, and the vibration is more vigorous, of course. Now we can say that those molecules are now in the gas state, and once again temperature will start to increase. So that's the overall curve. We have solid that will reach a melting point of 0 degrees Celsius. Then we'll start the melting phase, where temperature remains the same but energy or heat is still absorbed by the molecule in order to break the bond, overcome this force between them, if you want. Okay, once they turn into a liquid, once again the system will start to increase the temperature and absorbing heat, of course, linearly. So it's like as heat is increasing, temperature is increasing as well. Okay, until the molecules will now reach the boiling point, which is the point where they evaporate. And so during the boiling process, once again temperature remains the same, energy, heat is still absorbed by molecules to overcome the force of bonding between them, and so all of it will turn into a gas. We can notice few important stuff. Number one is something that I already mentioned, which is that this represents a linear relationship. So we have a linear relationship between heat and temperature, and that's once again related to the concept of increasing temperature means increasing kinetic energy. Heat depends on kinetic energy and potential energy, so increasing kinetic energy means that we're increasing the heat or the internal energy of the system. Second thing that we need to know is that if we compare the steepness of the slopes during the phases solid, liquid, and gas, we can notice that it is not the same steepness. So let me take, let's say, this slope from the liquid, compare it to the solid. You see how it's steeper? And if I take the gas, compare it to the liquid, it's less steeper than the liquid and less steeper than the solid. So why is that? Why do you think we have different steepness of the slope? When I say different steepness, means different temperature increasing, rate of increasing of temperature to the energy. Okay, so the steepness of the slope depends on two things actually. It depends on the mass, so how much mass we're dealing with, and depends on the specific heat capacity. So we already know what's specific heat capacity. Specific heat capacity is how much in joules needed for the system to increase the temperature of 1 kilogram by 1 degree. Okay, so let's see which factor here affects the steepness of the slope. If I count how many particles I have to see how the mass, whether the mass will change or not, you can see that we have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So the mass remains the same, which is very logical, because we are not changing the mass of the system, we're just changing the arrangement of the molecules in the system. So since the mass remains the same, this means that the specific heat capacity here is the thing that will change or affect the steepness, how much temperature is being raised to the energy or heat applied to it. So I was saying that the specific heat capacity of ice and water and steam, it's not the same. And we can see this by comparing the slopes, yeah? So if I copied the slope of solid and the slope of a liquid and the slope of a gas, and I have them over here. So this is the solid, okay, and that's the liquid. And this is the gas. Okay, so what can we notice? We can notice that liquid is the steepest slope, which means that water will have the greatest specific heat capacity. Gas has the least steep slope, which means that steam has the less, among all three, the less specific heat capacity. So the temperature increases more slowly during phases. It increases the slowest during liquid. It increases the fastest during gas. And that's due to how each and different ice, water, or steam have different specific heat capacity. Okay, so fourth thing that we noticed is third thing that we noticed is that the horizontal line at 100 degree is much longer than the line at 0 degree. Okay, so if we compare the length of the line, if we compare the length of the line during melting and the length of the line during boiling, you can see how during boiling it's much longer line than the melting. This means that it requires more energy. Yeah, so because it's called the enthalpy of vaporization of water is greater than the enthalpy of the fusion of ice. Last thing I want you to know is that this specific melting point and this specific boiling point are called the latent heat of fusion and the latent heat of vaporization.